So X is the intersection of OAB and AC, whereas here E is the intersection of the perpendicular bisector. So it's not like, is it really exactly the same?
Yeah, you can just draw circle AOD and you will see it passes through E.
Oh, it's AOD instead. Okay.
Yeah.
That makes sense. And then we know it's cyclic, so because O is the midpoint of AD, O is the midpoint of arc AD, and this is an angle bisector. Okay, so that's how it's equivalent. So yeah, it's the same thing. All right, this is a riddle. This looks easier, but still, I want to see if I can get something easier. So like this one looked kind of fun. Let's do this one. We have a triangle ABC, and we take the midpoints of arcs AB and AC, and then 2 points. So first I'm going to draw X and Y. So so this is Y and this is X. And we draw the midpoints of arcs AB and AC. So I don't know if I want to draw angle bisectors. That would probably be good. Let's move this out of the way. So if I move X here, so this is M, and this is N. And then MX intersects the circle at Q, and NY intersects it at P. And we want to show that the intersection of PM and NQ lies on the angle bisector. So that point right there, which is the same as saying that A, I, and B are collinear. This almost looks like Pascal's theorem a little bit. Right. Looks like if we apply Pascal's theorem right, maybe it would help. Oops. So MBQ and NCP, what happens if we use Pascal's theorem there? We have I, D, and then we would want BQ and CP. We'd want to see where they intersect, right? I guess it's the same as saying BQ and CP intersect on the angle bisector. But that doesn't look true, so I'm missing something.
BP and
Not
CQ.
BQ, it's BP and CQ, not BQ and CP.
Okay.
Yeah, that looks right.
All right. So we know that these are collinear. We want to show they're collinear with A. We also want to use that XY is parallel. So yeah, if we really wanted, we could hide MP, NQ, and point D. So let's see, we could try the angle bisector theorem. We could also try to show it passes through the midpoint of arc BC. That's equivalent. So AX over XB. Any parallels we could draw? Oh, okay. So AX over XB by the angle bisector theorem, that's BQ over AQ. And so that has to equal CP over AP. BQ over AQ is CP over AP. I don't know if that helps. So yeah, I wonder what would happen if we did this. Like, we drew this, and this. Oh, I don't think that does that much. Hmm. So I stays fixed as X and Y moves, P and Q move. I want to show this lies on a bisector. What's that equivalent to? Is there like a degenerate form of Pascal? Because IMAN is a kite, right? By the in-center X-center lemma. So AI is perpendicular to MN. If we could show that this is perpendicular to MN, that would solve it. I kind of like that way of doing it.
We can you just use the trigonometric form of Ceva to prove it?
That I is perpendicular to MN.
No, I mean, we can prove that AI and E is collinear by proving that AI, BE, and CE are concurrent.
Okay.
So by the trigonometric version of sine, we need to prove that sine of EBC over sine of EBA is equal to sine of ECA over sine of ECB, I think.
Okay.
We have sine of EBC is actually sine of PAC, and
Okay.
sine of EBA is sine of PCA. So that ratio is equal to PC over PA, which is YC over YA.
Okay.
So we
So,
do the same thing.
all right. So let me write this up. I actually thought about it differently. Let me before I write it up, let me just think about it. So I was thinking maybe we could show that IM squared minus IN squared is EM squared minus EN squared, and IM equals MA equals MB. Then for E, yeah. So yeah, I'll go do it. Yeah, I think Trig Ceva I think is the best. So let BP intersect CQ at E. E by Pascal's theorem, I, E, and D are collinear. Say, let PM do at D. Okay. And then now we'll apply Trig Ceva. So we want to show sine EP. All right, see you, Martin. Thanks for joining us. Yeah, sorry we didn't get through too many problems yet, but yeah, hopefully next time we'll get through more. So yeah, thanks. So sine EBC over EBA. That's going to equal sine PAC over sine PCA. So I skipped a couple steps here, but I'll write it down in just a second. So, and that is PAC. So that's PC over PA, which is equal to CY over YA. So yeah, this pretty much solves it. So it's a good idea. It won't put it on a different line. Let's see. Let's see if this works. But now it's all weird because it has an extra line. Okay, let's see. I'll just live with it. There we go. So and cy over ya. So cy over ya is bx over xa. Okay, so we have, and then I'll say similarly sine of ECB over sine of ECA. Is equal to bx over xa. And that implies that this times EBC times sine of what is it? BAI over CAI equals 1. I don't know if I'll just leave it like that for now. So by Trig Ceva, Trig Ceva A, I, and E are collinear. And that means that D lies on the angle bisector BAC. All right. All right, I'm going to move on to the next one. So yeah, sometimes Trig Ceva is just magic. This one looks like an easier one. So yeah, we could do one easier one and then maybe go back to a harder one. So the altitudes concur at H and whoops, sorry. And then we have a random point on the circumcircle of ABC. So we have D, whoops, DEF. Looks like Robbie's joining. And we draw the circumcircle of ABC. Hey, Robbie, thanks for joining us. T lies on EF. And XDHT is cyclic. So X is any point. We draw the circumcircle of XDH and we see where it meets EF. Let's see if we can make it better. Call this T. And we want to show TH is tangent to DHM. I forgot to draw M. XH intersects DEF at M. Okay. All right. So, all right, see you next time, Boomy. Thanks for joining us. So you have this and this and all right. Oops. All right. So yeah, X is any point on the circumcircle. You let XH meet the 9. So this is a 9-point circle. So really M is going to be the midpoint of XH actually, by a homothety. Because a homothety about H takes a 9-point circle to the circumcircle. So we have the midpoint of HX. Maybe it's worth drawing these other points that you get when you reflect H. So I might as well draw them. I don't think it complicates the diagram too much. And call it PQR. PQR. So we want to show TH is tangent to this circle, THM. Is that true? Did I draw everything right? Yes. So that's the same as saying that THM is HDM, which is HPX, which is APX. Okay, so basically we want to show APX is equal to THX. But THX is, so what's cyclic? THX is TDX. So we want to show TDX is APX, which is the same. TDX equals DPX. So I think it's the same as saying that if we drew the circumcircle DPX, we want to show the tangent at D passes through T. Yes. So that's another way to show it. Actually, AT passes through the intersection of HDX with ABC. But you mean HDX? This is HDX with ABC. Okay. So okay, so you're saying it passes through this point. Wait, let me read what you wrote one more time. AT. So it passed through this point is what you're saying. Wait, is that true? Yeah, interesting. Okay. So how does that solve it? Because so AT. Oh, did you just do an angle chase to show what I was saying, or oh, the angle chase I did. THX equals APX. Okay. THX is 180 minus TGX, just 180 minus AGX. So how did you know that these are collinear? Let's think about that. By inversion at A. Oh, because AHEF is cyclic. So I guess you're inverting about A, doing an inversion about A with radius, yeah, root H. Okay. Yeah, let's see if we can do it just by angle chasing. So or I could use inversion. So do you also want to reflect about the angle bisector or just the inversion? Just invert. Okay. Okay, so H and D, so EF gets swapped with BC. So T. Okay, so this circle would go to so H and D just get swapped. And so that circle, yeah. All right, so I'm going to copy a lot of what you put. Invert about A radius. ABC maps to line EF. ACF stays the same. All right. Okay. So AT and G, we'll say equals G. Okay. And then, yeah. Well, he inverted about A, right? But maybe there's another way to do it with H, inversion at H. So AT and G are collinear. And then once you have that, then you show the angle chase. So THX equals APX, which is HPX, which is HDM. So yeah, let's write the angles just to make it look better. All right, so this one was quite a bit easier. Split it up into 2 lines. Now I'll move on to the next one. So TH is tangent to BHM. I should write, I mean, we use that a homotopy about H takes HTM to HPX. So I'm gonna just write that out. Oops. Just for the people watching. All right. So I'll move on to the next problem. Do you guys want to try a riddle this time? Or this is a fun riddle with a square. Oh, you guys want to try this one? Otherwise, we could do. Oh, actually, both riddles look kind of interesting. Yeah, Bertino is kind of hard, so I wouldn't doubt that he made that. Let's do this one. So we have a triangle ABC. We draw the asymedian, and we draw the midpoints of AC and AB. All right, so here is the symedian. And that gives us a harmonic quadrilateral, ABCL. It's another way to say it. It's harmonic. This is L. And then we have the midpoints. Whoops. These are N, M. Oh, oops. M is the midpoint of AC. N is the midpoint of AB. We draw the centroid. Wait, I'm going like crazy here. This should be N. Let's see. Okay. We draw the centroid of AMN. Whoops. Should be G. That's 2/3 of the way. So yeah, if I really want, I could draw the midpoints of these two. Why not? And AG intersects GMN at K. This looks like a homotopy of some kind. HIJK. So we want to show the radical axis of CNK and BMK bisects AL. All right.
We should note that the midpoint of AL is the dumpty point, and it has many properties.
Okay. Yeah, it's the midpoint of the symedian chord. So yeah, it's a dumpty point. So we should probably draw the center of this. Oh, I like what it's naming the points. We know that that's OJB. DC is cyclic. And we have this is cyclic also. So that's looking pretty good. It's a lot of information here. So we want to show the radical axis of CNK and BMK bisects AL. So what's another way? I mean, we want to show that J lies on the radical axis of those two. That's another way to say it. Okay, so we have CNK. BMK. And we draw KJ. And indeed, that's the radical axis. Okay, so can we calculate the power of J with respect to those circles? That is the question. Maybe we could use Casey's theorem. So I just don't know the center of those circles are this thing. Yeah, Casey's theorem might be tricky. Well, maybe not actually. So let's draw what's the center of this circle right here? Q. The center of that circle. Does that lie on the other circle necessarily? I don't think so. No. And bright out. Maybe there's another point that lies on this. So yeah, K is defined in a very interesting way. There's some special point. Let's see if AO is collinear with that point or something. No. Is GJ, I think GJ, maybe not. I was going to say GJ is perpendicular to MN. No, because J is like a symmedian. It's not necessarily true. Yeah, I'm going back to trying to use Casey's. So let's see, the center of this circle is the midpoint of OD. That's Q. we draw this point right here. So the power of J with respect to CKN, it's basically by Casey's theorem, it's 2QP times the distance from J to CR. I don't know if we can calculate that easy. Yeah, what can we calculate? The distance from J to So I think AJC is tangent to AB and AJB is tangent to AC. That's like a famous theorem. Yeah, the riddles are so hard and the middle riddles are so easy. We need like a semi, we need a sort of middle riddle. Yeah. Yeah. CKN. Yeah, see, the thing is there's like no, so there's this circle right here. And there's this circle, and Kn is the radical axis. So what's the center of this circle? It's S. Now I wonder a homotopy about A takes, so these circles are tangent by homotopy at A. So let me try this. What if I let AC? Is there anything that point K has to do with the triangle of ABC? So it lies on the median. Lies on the median of ABC. But yeah, I'm trying to think what else. Could it be the isogonal? Okay, we know these rays are isogonal, at least. I wonder what the isogonal conjugate of K is. So I think if you reflect, whoops. So if you reflect K about each side and take the center of that circle, I think that's the isogonal conjugate. Whoops. Reflect about line. So I'm going to take these three reflections and then I'm going to take the circumcenter. Let's see where it lands at. What? That is not what I expected. If you reflect a point over all three sides and then take the center of that, is that the isogonal conjugate? I thought it was for some reason.
It is, but you just made a mistake while reflecting.
Okay. Yeah, I think K double prime is wrong. So let's try that. That should lie on this median. It's point T. And yeah, I don't know if there's anything really special about that, other than that it lies on this median. Okay, yeah, we could try some other problems. Do you want to try a middle riddle the last 30 minutes? Or let's see what else we can do. Yeah, I agree. These riddles are really hard. I'm hoping they come out with the IGO. Yeah, they're too hard. We've solved a couple in the past. Okay. Let's see. So actually, spot.com. Let's see what's on this website. Do you have a contest that you're interested in? Let's see what's recent. So this is 2021 IGO. Recently posted. Want to take one from China?
Yeah, let's try one.
Okay. All right, let me clear out this. These are tricky. Let's see. What's a good one? TST is harder. Let's just try China Math Olympiad. China. Okay, so not the TST. What's international? For 30 minutes. Okay, so let's see. I'll just take a look at these middle riddles. Did we do this one? I don't think we did this one in the past.
How about we do middle riddle 241,
241. Okay.
the most recent one?
Oh, that looks good. Oh, it's at 10:30. It was just posted. Nice. All right. So we have a triangle ABC. And I'm trying to maximize the screen, sorry. It doesn't want me to. Close this. There we go. Somehow if I shift GeoGebra, then it works. So you have a triangle ABC in circle is tangent at D. B. AI intersects the circle at K. So that's the midpoint of arc BC. But yeah, the riddles, like, it's nice that there exists a collection of problems that are not that hard to state, but are really hard. But they're just so, like, before I found that Discord server, I couldn't even find a collection of problems like that. But now I know they exist. They're just really hard. So yeah. KIB intersects ABC at Z. And we want to show that KID, and wait, did I mess up somewhere? Yeah. This is actually very easy by configs. Wait, we want to show this circle. So this point.
No. K is not that point.
I think you drew K wrong.
AI intersects.
Notation there, it means like
Oh,
the K
diameter.
is point. Yeah, diameter AI.
All right, so I got confused there. So this would go through those 4 points. And so this is a Sharkey double point. And it has a lot of properties. So then KID. Yeah, I'm sure. Yeah, the Sharkey double configuration probably crushes this. Z. We want to show they meet here. And so Stefan, so is this just like an inversion about the in circle or something like that? Solves it?
I think we don't need to invert even. Just
Okay.
use configuration facts. So look at circles KID, KAI, and ABC.
Okay.
And we can take radical axis theorem to see that KI, FG, and D and the intersection of KID and the in circle.
Okay.
Wait, actually, I just have to think on which circles we're doing the radical axis. But HD, FG, and KI should concur.
HD, FG, and KI. So KI meets FG at the perpendicular. So basically,
Exactly.
if we can show DH is perpendicular to FG, is that obvious? Let's think. DH, is that just an angle chase to show DH is perpendicular to FG?
No, but I think it is.
Not
We
that
can
hard.
show that DH is perpendicular to FG by radical axis theorem, as these concur.
Okay. Because so the radical axis on this circle. Oh, it's just the radical axis theorem. Okay, I see.
Yeah. And
So-
then we use another fact that if you intersect AH with the circumcircle ABC,
Mhm.
then that would be the mixed linear point.
Okay.
And it is just left to show that Z is the touch point of mixed linear circle. And I believe it is not hard.
Okay. So yeah, I'll summarize the solution really quickly, just in the text, and then we can try another. So FG, by the radical axis theorem, FG, DH, and KI concur. FG, DH, and KI concur. By a well-known theorem, AH meets ABC at the mixed linear touch point. And then, yeah, it's not hard to show that that's cyclic by an angle chase. Let's think about that for just a second. I'll say Z prime. And we want to show KIDZ prime is cyclic. Let's think about that. So this passes through the midpoint.
Can you connect, let KD meet circumcircle ABC? It should
Okay.
be the midpoint of arc BC.
Yes.
It just negotiates now. When you define point L, you just need to calculate angle Z prime ID and Z prime KD.
I was actually, that's interesting. Z prime ID and Z prime. I was thinking it's just Rhimes theorem because we know this passes through the midpoint of arc BAC, and ML is parallel to ID. But yeah,
Yes, that's nice.
okay. But you don't need you could do an angle chase even without that, right? Interesting. Okay. So M, I, and Z prime are collinear. And then since ML is parallel to ID, implies KIDZ prime cyclic. And then Z prime equals Z. All right. Let's see what else we can do. How much time do we have left? About 20 minutes. Do you want to try another middle riddle?
Maybe we can try to finish the first one.
This one?
Maybe.
Okay. Yeah, let's see if we can do this calculation. So if OH intersects BC at R, then we want to show that the cross ratio equals this. How would you bash that? So we'd have RB over RC. Can we use Menelaus on that? So RB over R, we know RB over RZ is RH over RY, which is GH over CY. That's probably helpful. Because these are parallel. But that's RB over RZ. Then we need RZ over RC. So but we also kind of know that because RZ over RC. Yeah, so we could find our B over RZ and then our C over RZ, and then we could kind of take a ratio. Maybe that would work. I kind of like that idea. Let me write this on paper. So RB over RZ. That would be HG over CY. And then RC over RZ is HG over BK or BX. So RB over RC is BX over CY. So we want to show that BX over CY times GC over GB is this. Is BGX? No, they're not similar. So yeah, how do we calculate BX and CY? That's the question, or the ratio. So we know the average of BX and CY is OF. And OF is half of AH. So CY is 2OF minus BX. Get another little piece of paper. Yeah, I didn't know this lemma. It's a good one. Yeah, it makes sense. If t is actually on the perpendicular from A to BC, then this would be 0 over 0. So wait a sec. Now I'm wondering something. Wait, so let's say t was actually on the perpendicular from A to BC. Then TB squared minus TA squared equals TC squared minus CA squared. So this ratio would be 1. Oh, and they would intersect at the point at infinity. I see.
There is no way of doing this without a bash.
Yeah. Do you know like how the bash would work, or
A complex bash should work.
Yeah, it really looks like the complex bash should work here.
You have a very neat point H in the complex bash, and you have to really bash it to get the point R.
okay, BG. Yeah, so we're trying to calculate BGRC and show it's equal to this. But so RB over RC, we could find RB over RZ. That's just GH over CY. So, and we could do the same with RC and RZ. So when you divide the two, I think you just get BX over CY, right? When trying to do RB over RC. ZB over ZC, yeah. So like, is it true that RB over RC is BX over CY? That's what it looked like to me. And then
Yeah, but we are trying to get rid of these points X, Y, K, and L. They're much
Yeah.
harder to work than just point R.
yeah,
For example, I think this may work like we should take ABC as a unit circle, and then we can just compute T by rotating BC around C for 60 degrees.
okay.
Okay. And then we can find Z from this here formula, BZ over CZ is equal to this.
Okay.
Then we have Z, and then we just have to compute the modulus of AZ and TZ. I
Okay.
think there will be like much calculation, but I'm not sure.
All right.
It's working, but I don't have any idea how big will that how much calculation we would need.
It would need to do that. Okay. Yeah, I'd rather not type up the whole complex bash here, but it seems like an interesting idea. Like you call this the unit circle, and then you rotate this by 60 degrees. Like you multiply by CIS 60. C. I was. But yeah, that is an interesting lemma. So yeah, if you let OH meet BC at R, then this cross ratio is equal to this. So is there a way that we can interpret this? So like AB squared minus BC squared. Yeah, I'm trying to think of a way. So that's kind of like if we tried to make a right angle. So like we try to see where this meets this. And this right here would be that difference. Hmm. Okay, so yeah, it might just be a longer calculation. Let's see what else. See what other problems we can find. I'll try the, oh yeah, I deleted the square one. That looked kind of interesting though. So yeah, we have 10 more minutes. This is a kind of long middle riddle. Oh, did we try to do this one before? I think we did, right? I don't remember. But yeah, I think we took a look at it. Yeah, we're not going to solve these in 10 minutes, but oh, this one was also at 10:50 today. Okay, so we have a median point K. Maybe we could just take a look at these for a little bit. K is the symmedian point, G is the centroid, and O is the circumcenter. P lies on OK. The Euler line of the pedal triangle. That sounds complicated. The Euler line of the pedal triangle. Let's see what else we have. The square one. Yeah, I'll just draw the square one up. That one looked interesting. So where is that? Okay, that's, oh yeah, this one. So yeah. Like, yeah, this one does not have that hard of a diagram. So let's see. Yeah, I just reset my computer because it was having issues. So it's going to start out showing like the grid and stuff. Get rid of it. Okay, so yeah, I have to change it so it locks the settings. Okay, so let's do this. So can you guys see it when it says your internet connection is unstable, or you guys don't see that?
Sometimes.
Like, could you see it on my screen right now? Like, I think the Zoom doesn't show you guys that I saw that.
No, it doesn't. I don't see it.
Okay. All right, so ABCD is a square. And I haven't drawn a square in a really long time. Should have drawn it the other way. All right, so we have a square with center O. and P is any point on the circumcircle. Let me maximize this. Sorry. Let's try to maximize it. Let's go back to this. Sometimes it just doesn't like it when I click the maximize. Oh, well, we can leave it like this for now. There we go. So O is the center. And P lies on the circle. And AP intersects BD at a point. BP intersects AC. So those both go through the center. So we have X and Y. And then we project X and Y onto CD. That's P and Q. Oh yeah, they use the letter P twice, so that they got confused here, but BP intersects AQ. So let me rename this so I don't get confused. Call it R. So this should really be P and Q right here. So this is P, and this is Q. Oops. BP intersects AQ at K. And XP intersects YQ at L. So we have a K. And L. Oh, we want XP and YQ. We need an L. And we want to show OKLP is cyclic. So yeah, we're out of time. I just want to draw it up, see what it looks like. I think.
Why doesn't it look right?
I think it's really OKRP. Well, no, yeah, because the problem is that they accidentally. It should really be like this. They accidentally put P twice in the statement. So, and then it's correct. It's interesting. So yeah, like it doesn't look like that complicated of a diagram, right? So it's a riddle. But yeah, maybe it's harder than it looks. I don't know. Oh yeah. All right, so we're out of time today. I will try to find some other problems. Oh, Ryan says he knows this one, or he's seen it before. All right, I'll try to find some problems from competitions next time to mix it up so that we try some different things and get, oh, it's a test in Vietnam. But yeah, I'll try to make it so that, you know, we get more intermediate difficulty problems rather instead of the super hard ones and super easy ones. But I want to thank everyone who participated. So if you'd like to join us in the future, feel free to email me at mgreenb801@gmail.com. We meet every Sunday at 8 a.m. US Central Time. So mgreenb801@gmail.com. It's in the description of my video. So thanks again for watching and have a great day.